Welcome to today's meeting of the QED-C Standards and Performance Metrics Technical Advisory Committee. Today we are joined by our cohort of summer interns, Sunny, Avamita, and Anish, who will introduce themselves and describe their work for the committee this summer. They've been maintaining and expanding QED-C's open source suite of application-oriented performance benchmarks for quantum computers. And I want to extend a thank you to the members of the Standards and Performance Metrics TAC who have mentored or collaborated with them this summer. And in particular, I want to take a moment to thank Tom Lubinsky, who leads this quantum computing subcommittee and was really instrumental in leading our fourth cohort of summer interns. So thank you, Tom. I encourage everyone to stick around for the hour to learn something and to enter any questions you may have into the chat. We're going to save those questions until the end to make sure we get through all of the content today. And encourage you, if you're available, to stick around to the end of the hour or even into the next hour. We'll continue the conversation. So thank you for joining today. And Tom, over to you.
Yeah, thanks, John. Yeah, I think we should just jump right into the presentation, but I did want to just give a big shout out and a great big thanks to the, this set of interns over the summer. They've been doing absolutely fantastic work. I've been extremely happy. I think that what I could say is I just wish we had them for a few more months. We'd get a lot more done. So yeah, they've been doing a great job. I also want to thank the other members of the Standards TAC. We've had a lot of contribution from many other members in helping make this project. It is the fourth summer that we've done this, and I'm really happy to see the results that are being created here. So with that, why don't we just jump right in, and I'll turn it over to Sunny and get started.
All right, thank you, Tom and John. I'll indeed get started. Welcome, everybody. Today, the other interns and I will be presenting our work on creating and refining a comprehensive Hamiltonian benchmarking suite. So as a general introduction, we're going to go through and introduce ourselves. I'm Sunny Rappaport. I graduated from Cornell last year, and I've been taking a gap year to do some internship works. I first did an internship at INQ, and now I'm here with the QED-C. And in both cases, I've been really interested in near-term applications of quantum computers and how they'll develop and mature. And I'm excited to start my PhD at Boston College in physics soon.
Hi, I'm Anish Giri, and I'm a senior at Vanderbilt University doing physics, computer science, and math. I am working on some other research labs here related to many body systems and some other experimental physics projects. And yeah, this is my first internship experience directly related to quantum computing, and I'm excited to present to you our work.
Hi, I am Avamita. I am a PhD student in computer science at Penn State. My work for my PhD is mostly in quantum error correction. So when I got this internship, I'm trying something new here, quantum Hamiltonians, very new to this. And I hope you like our presentation.
All right, so let's see here. Just as a general outline of what this presentation is going to be about, in the first section, I'll continue explaining and talking about the Hamiltonian benchmarking suite we made, briefly introducing the Hamiltonians we're using and in what context. Next, Avamita will talk about exploring our benchmark suite with HamLib, which is this huge library of different Hamiltonians. And we'll elaborate on a scalable performance benchmark that we developed. And finally, Anish will talk about using our Hamiltonian benchmarking suite to benchmark energy and observables from the circuits that we can produce. So first section, Hamiltonian benchmarking suite. So as everybody knows, the QED-C really does support the quantum industry. There's a lot of interest in quantum since it can solve certain problems much, much faster than classical computers, potentially exponentially faster. And the QED-C is this organization that helps accelerate the growth of quantum technology by facilitating collaboration between many, many different organizations. Here I've written 250 organizations and different companies. For instance, this summer, just off the top of my head, we worked with Sandia Labs, Lawrence Berkeley Labs, and even in all of the standards committee meetings, we've been working with companies like IBM, IonQ, Quantinuum, etc. And it's been really great to work and make things happen with all these companies and organizations, even as just an intern. So one of the things I would like to highlight and focus on during this presentation is the QED-C's standards and benchmarks development, in particular, the application-oriented benchmarks. So the real strength of these application-oriented benchmarks is that they directly address problems with practical significance by essentially running the problems on a quantum computer and seeing directly how well they do. Other benchmarks definitely have their pros, but the application-oriented ones sort of directly are addressing interesting use cases. In our suite, we already have 15 or 16 or so benchmarks already developed. You can sort of scan that QR code. I'll have it in a few other places in this intro section, and you can see the work done on the GitHub so far. These benchmarks gauge progress across multiple different progress domains or problem domains, I mean. And this summer in particular focused on really developing the Hamiltonian simulation benchmark. So here's just an example of what the application-oriented benchmarking suite gives you. You can see here on the y-axis, we have number of qubits essentially. And on the x-axis, we have a normalized count of the number of gates in the circuit. What we're plotting here essentially is a fidelity or how well the algorithm is running at certain qubit depths and widths. And you can see here for this noise model rated at a quantum volume of 2048, as you use more and more circuit resources, the algorithms get worse and worse. And obviously, as quantum computers get better and better, we hope to see all these squares become blue. And that's what's happening, I think. So starting to focus more on Hamiltonian simulation and why we focused on that this summer. Hamiltonians are pretty central, for example, to physics. The Hamiltonian generally describes the dynamics of a system. For example, let's say an American football, the Hamiltonian of a football would describe its trajectory and energy after you kick it and send it soaring through the air. The same sort of thing applies to quantum Hamiltonians. For example, a quantum Hamiltonian of this 2D spin lattice down here would describe the sort of quantum rules of how these spins align themselves and evolve in time. Now, the challenge with quantum Hamiltonians is that, unlike classical ones, it takes exponentially scaling resources to describe them on classical computers. And that's where quantum computers can come in. There's been a lot of work over the past few decades in showing that with quantum computers, certain quantum algorithms can provide a significant theoretical advantage in simulating them. Unfortunately, because quantum computers are still a burgeoning technology, this advantage has yet to be seen. So just as a bit of more context as to what sort of quantum Hamiltonian simulation we're looking at, we use Hamiltonian simulation with trauterization. For any Hamiltonian simulation, the goal is to evolve an initial state using this Hamiltonian after some time t. Here I've written out this equation that essentially explains what the algorithm does. Starting with this psi at an initial time, we apply this evolution operator u of t. there's a lot of technical details involved, but essentially what trotterization does is approximate this U of t and applies it as this trotter unitary right here. So first you apply the initial state, use this trotter unitary to approximate the evolution, and then you can measure this Hamiltonian evolved state and use it either in other algorithms or just use that to get an approximation of the quantum state. So what's interesting about the trotterization algorithm is that the theoretical performance, or how well it could possibly do, is well understood. There's, in this link, I essentially linked to a paper where they prove some upper bounds and how well the trotterization algorithm will perform on a noiseless quantum computer. But it's sort of difficult to estimate how well it would practically do on hardware. So what our benchmark really allows users to do is to test the Hamiltonian simulation circuit on hardware up to any number of qubits. This provides useful comparison metrics for comparing across different quantum computers today, and also helps you keep track of progress towards quantum advantage for this particular algorithm. And in general, this suite allows you to keep track of progress to quantum advantage for all the quantum algorithms included. So over the summer, we had to basically wrestle with the question of which metrics should we include for the Hamiltonian simulation algorithm. And we settled on it depends, essentially. So we give users multiple options. The first sort of option is application oriented, and it's pretty straightforward. It's just saying essentially, does your quantum computer accurately perform Hamiltonian simulation? The second is a little more complicated, but I think it'll make sense when I explain it. As I explained before, the algorithm theory of trotterization already gives you upper bounds and how well it should perform on a quantum computer. But how well it performs on a real quantum computer with noise is more difficult to predict. So you might just be interested in more purely how well does the hardware run Hamiltonian simulation, or how well does the circuit perform itself? Because of this complexity, we've developed several methods to test Hamiltonian simulation. In this section, I'll go on to explain methods around the state fidelity after a single circuit is executed. Later on, Anish will explain how we've used Hamiltonian simulation circuits to generate energies, observables, and how we can use that as a metric. So here are the methods we use to test the fidelity of a single circuit after it's executed. In method 1, we primarily test the hardware. In method 2, we primarily test the hardware and the algorithm, but as I'll explain a little later, on a noiseless background, method 2 just shows you the algorithmic error, or the trotterization error, as I note down here. Method 3 is also a test of just the hardware, just like method 1, but as I note down here, method 3 is scalable up to any qubit size, while methods 1 and 2 are not scalable. So to put more context into the scaling comment, I'll sort of explain how the methods work in more nitty-gritty terms. All the methods are based off of the original Hamiltonian simulation circuit, but in method 1, what we do is run this circuit in both the noiseless Qiskit simulator and the target backend to produce the fidelity. In method 2, we only run the circuit on a target backend, and to produce a correct distribution, we run it on this classical Hamiltonian simulator, which exactly performs the dynamics. So there's no trotterization type approximation being done there. It's exact. Note that this means if the target backend is noiseless, we should only get the trotter error, since this result is perfect, whereas the target backend will only hold a trotter approximated circuit. Finally, in this third case, the special mirror circuit case, we use this Hamiltonian simulation to generate a mirror circuit. The trick behind the mirror circuit is essentially we evolve the state forwards using the trotter unitary, then backwards with an inverse trotter unitary. And we should get the initial state distribution after that. Because we already know the initial state distribution, there's no need to use a classical simulator. And we can scale up to any number of qubits since we'll always know the correct answer essentially for free. So given all that and that general guide as to the methods, I encourage everybody here to run the benchmarks yourself. I've included a QR code here and a link that you can't click unless you download the PowerPoint here. Everything is in the master branch now. If you want to run our benchmarks in the form of Jupyter Notebook, you can go to this file. Otherwise, you can also run our benchmarks in the command line format. And all of our work you can find in the hamlib folder. So just as an isolated example of what the Hamiltonian simulation benchmark results look like, you can see just like the other volumetric plots, we present the result fidelity at different circuit sizes. Again, as more circuit resources are required, the worse the results get. And here we have this additional plot that shows different depth metrics, different time metrics, in addition to the result fidelity metrics. So that's all that I have to present, and Avamita will take it away in exploring different Hamiltonians with hamlib.
Okay, thank you, Sunny. Hello, everyone. Okay, so far, Sunny has talked about all the different methods that, of benchmarking that we are going to use in this project. So I'm going to start by talking about, exploring the benchmarks with hamlib. But before we go there, let's see how different methods compare to each other. Okay. So we will take a look at these two plots. The first plot is for the Heisenberg model, and the second is for the Fermi-Hubbard. So I'm going to talk about, what these models are in a later section, but this slide is only about comparing the three methods and how they look like in general. So method 1, as described by Sunny, is representative of hardware error only. Okay. Method 2 is the error, which is a combination of hardware as well as algorithmic or trotterization error. And method 2 noiseless is the algorithmic or the trotterization error only, and therefore it has the highest fidelity. So if you look at it, a method 2 should be a summation of method 1 and method 2 noiseless. Okay. Now, the third method, which is the mirror method, is also representative of hardware error. But you have to realize that since it's the mirror method, it also has double the circuit depth apart from any other methods. And since the circuit depth is double, the fidelity that is being captured here is also the lowest. Therefore, we have to normalize the fidelity. So in order to normalize this fidelity, we take the square root of the fidelity values. And once we do that, theoretically, it should match the hardware error of method 1. So in the following slides, all the fidelity that is represented by method 3 are the normalized or the square root values. All data shown were executed on the air simulator with noise equivalent to quantum volume 2048. Now, if you look at these plots, you would notice that there's a line for each of these methods, and there's this colored halo around those lines. Now, for every Hamiltonian model, there are many parameters that we can vary. I'm going to talk about the parameters in upcoming slides. But once I vary those parameters, the fidelity also changes. So this halo kind of shows that we are looping over all the parameters that are available for this particular case. Okay. And this is the structure that we are going to follow in the rest of the slide as well. Now, since method 3 is so important that it's scalable as well as it portrays, the hardware error, we are going to talk about a few variations of method 3. The first is the generic kind that Sunny already described, where we have the initial state, the Hamiltonian, and the inverse of the Hamiltonian, thus giving us double the circuit depth than the others. The next kind is what we call as the random poly or the multiple random poly. We have the initial state, the Hamiltonian, but between the Hamiltonian and the inverse Hamiltonian, we have a set of random polys. So this set of random polys is responsible for, not nullifying errors in the system, and therefore giving us a truer sense of what the hardware noise looks like. So if we have only one random poly, we call the variant random poly. If we have a set of random polys, we call it multiple random polys. So in our experiments, when we work with multiple random polys, we have used 10 different random polys and averaged over them. Now let's talk about Hamlet. It's a library of Hamiltonians, and as the name suggests, it is exactly a library of Hamiltonians. It provides diverse Hamiltonian models, enabling broad benchmarking across quantum systems. The idea behind Hamlet is standardization and compatibility. So using this, it kind of standardizes the benchmarking, making cross-study comparisons easier. It facilitates innovation. So Hamlet's rich data set accelerates quantum algorithm and hardware development. And finally, it has an extensive content coverage. So Hamlet includes models and problems like the max K-SAT, the transverse field Ising model, the Heisenberg, the Fermi and Bose-Hubbard, and even traveling salesman problem. We choose 5 Hamiltonians from this vast library. The first two are the Fermi and the Bose-Hubbard models. I'm not going to go into the very details of what these models are. We are just going to go a brief overview and mainly focus on the benchmarking part. These models describe the fermions and the bosons' movement and interactions on a grid using periodic boundary conditions. That is where the grid's edge connect to form a continuous loop, and encoding methods like binary strings to represent quantum states. So encoding schemes are in general responsible for translating the particles' movements into quantum states. Then we have the quantum Heisenberg and the transverse field Ising model. These two models show how spin interact in a material using periodic boundary conditions that connect the ends of the spin chain to simulate an infinite loop. The fifth problem that we have is the max 3-SAT problem. This problem involves finding the maximum number of logical conditions or clauses that can be satisfied in a formula with the clause ratio, which is the number of clauses compared to variables. And the clause ratio is responsible for indicating the complexity of the problem. So now that we have talked about the 5 Hamiltonians, we are going to talk about the parameters that we can vary in each of these Hamiltonians. Okay. For the first two, which are the Hubbard models, we can vary the number of qubits, the periodic boundary conditions, that is whether the circuit has periodic boundary conditions or whether they do not, and the encoding methods. For the next two, which is the Heisenberg and the transverse field Ising model, which in later slides we'll call TFIM, we can vary the number of qubits and circuits with or without periodic boundary conditions. And the fifth is the max 3-SAT problem, and here we can vary the number of qubits and the clause ratio. So now let's start with the benchmarking. For the Hubbard models, we are going to first focus on whether the circuit has periodic boundary conditions or they do not. So this is the plot that shows average circuit depth with respect to number of qubits for Fermi-Hubbard, Bose-Hubbard, PBC or non-PBC. PBC is obviously periodic boundary conditions. So the first plot here is for method 1 or method 2. Now this is because both of these methods have the same circuit depth. And the second one here is for method 3. Method 3, as we talked about before, is mirror circuit, and therefore it has double the circuit depth than method 1 or method 2. Now, if we, in general, if we look at these, depth plots, we will see that circuit without periodic boundary conditions have a lower depth than PBC. And Fermi-Hubbard in general has a lower depth than Bose-Hubbard. Now, if we look at the different fidelity plots for all 4 different methods, method 1, method 2, method 2 noiseless, and method 3, we notice that it's exactly the opposite of depth, where circuits without periodic boundary conditions perform better than the one with these boundary conditions. And the Fermi-Hubbard models in general perform better than the Bose-Hubbard models. Now, this is because that fidelity is inversely proportional to the depth, irrespective of, in what system we run this in. One thing that we want to notice is that if you see here, we have normalized the fidelity obtained from method 3 by using square root. So we will notice that how similar the method 3 plot looks with to the method 1 plots. Okay. This is the general structure that we are going to follow for benchmarking for all the other cases where we will have 2 depth plots for method 1 or 2 and method 3, and 4 different fidelity plots for 4 different methods. Okay. Now, moving on to the encoding schemes of the Fermi-Hubbard model. The encoding schemes that we use here are the Brevy-Kitov, the Jordan-Wigner, and parity. Again, we have the same depth plots for method 1 or 2 and method 3. Here we will notice that JW or Jordan-Wigner has a lower depth, and BK has the highest average depth. Okay. If we look at the fidelity plots, in general, they are inversely proportional to the depth, and therefore, JW performs the best, while BK has the least fidelity. The Bose-Hubbard model uses 2 different encoding schemes. Unlike the Fermi-Hubbard, we have gray code and the standard binary code. Here we notice that the standard binary has a lower circuit depth than the gray code, but the standard binary performs better when it comes to fidelity than the gray code. Now that we are done with the Hubbard models, we will talk about the Heisenberg and the TFIM. The only parameters that we can vary in these 2 models are whether the circuit has boundary conditions or they do not. And these are what the average depth plots look like. The orange lines here is the Heisenberg, which has a higher depth than compared to TFIM. And the dotted lines in general are the non-PBC kind, which has a lower circuit depth than PBC. On the other hand, we have 4 different plots which perform the opposite of the depth. So we see that the non-PBC has a higher fidelity than the PBC, and this is constant among not just the Heisenberg and TFIM, but also the different Hubbard models. The last is the max 3 set problem, where the only parameter that we vary other than the number of qubits is clause ratio. So as we discussed before, clause ratio is representative of how complex the problem gets. So we notice here that the clause ratio 2 has the lowest circuit depth, and clause ratio 5 has the highest circuit depth, which almost talks about that as clause ratio increases, the complexity of the circuit also increases. When we look at the fidelity plots, it's just the opposite. The most complex, which is clause ratio 5, has the least fidelity. Now, if you look at this particular plot here, which is for max resets fidelity for method 2 noiseless, or the trotterization error only, we see that the fidelity is perfect at all times. Now, we believe that this is because of the circuit construction of the max 3 sat problem in general, which gets nullified when we use method to noiseless, and therefore the trotterization error is non-existent, and we have fidelity of 1 at all times. So now that we are done talking about all the 5 different problems, let's look at all the models together. Okay. So this model has 5 different this plot has 5 different models that we have talked about so far. So here we can see that the TFIM has the lowest circuit depth in general, while the Bose-Hubbard model has the highest circuit depth, actually a lot higher than all the other models. When we compare fidelity, we notice that the TFIM has the maximum fidelity. Then we have Fermi-Hubbard and Heisenberg, followed by Max 3 sat, and lastly Bose-Hubbard. You would notice that how method to noiseless, which is representative of algorithmic error, it always has the least fidelity as expected, and how similar the fidelity of method 3 looks as compared to method 1. So now that we have talked about all the methods, we are going to talk about a scalable performance metric, scalable with respect to number of qubits. Method 1 is accurate, but it's not scalable. Method 3, on the other hand, is scalable, but it needs normalization to match method 1's accuracy. So we are going to talk about some strategies to make sure that method 1 retains its scalability while boosting performance. Comparing method 1 allows us to use method 3's results as a reliable indicator of hardware performance. So method 3's scalability kind of makes it useful for predicting hardware performance in cases where method 1 cannot be applied, that is after it passes some number of qubits. Method 3 square root or normalized aligns with method 1, making it a practical tool for scalable fidelity measurements and predicting hardware performance while keeping it scalable across a higher number of qubits. So before we go into comparing method 1 and method 3, we are going to talk about a few variations in method 1. First of all, we analyze different setups of method 1, including changes in the number of trotterization steps, K, or trotterization time. These are the 3 plots that we are going to look at. These belong to the Heisenberg, the Bose-Hubbard, and the Max 3 sat models. So the baseline or the basic method 1 that we concern ourselves with in all the plots is method 1 with K number of steps equals to 5. This serves as a baseline. Now, this is being compared to its inverse and a longer circuit of K equals to 10. Now, as we take a circuit with number of steps K equals to 10, we have to realize that the circuit depth gets doubled immediately. And therefore, it requires normalization, that is square root, due to the increased circuit length. Okay. So if we look at all these four lines, K equals to 5, its inverse K equals to 10 square root, and its inverse square root, we find negligible variation. So this proves that the normalization method that we are undertaking for method 3 is validated, and that is what is required for it to match with method 1. Another extreme setup that we also try is number of steps equals to 10, but with a very low time parameter. Now this results in a sharp fidelity peak very similar to method 3. So now we move on to comparing method 1 and method 3. We are only going to look at one plot here. It is safe to assume that for all the other models, the plots kind of look very similar. Method 3 with K equals to 5, which is the baseline, has double the circuit depth due to its mirror structure, leading to a very low fidelity, which is this maroon line here. And this fidelity needs to be normalized to make it comparable to method 1 for all other method 3 variants. The closest approximation, which is method 1, k equals to 10 with a very low time parameter, it aligns closely with the method 3, k equals to 5 square root, showing that method 1 can mimic method 3 under specific conditions. Now, method 3, particularly with random poly and multiple random poly variants, it offers a more stringent evaluation of quantum hardware by capturing more noise and errors. So therefore, method 3, with its rigorous fidelity assessment and scalability, provides a more accurate measure of quantum hardware capabilities compared to method 1, while being more scalable than method 1. So with this, I think I end the benchmarking section with Hamlet. I will let Anish talk about the rest.
Thank you, Avamita, and thank you, Sunny, for laying out the framework of all these Hamiltonians and explaining all these results that demonstrate the quality of the simulation. So far, we have only talked about the quality of Hamiltonian and the quality of the performance. But in the next few minutes, what I'm going to talk about is how these simulations run in terms of like execution of time, time execution and elapsed time. And I'm also going to talk about some meaning behind these observables and our future works that we are going to do further, or at least like that we plan to do further. So in this slide, what is equally important when we talk about these Hamiltonians is how fast these Hamiltonians or these simulations run. And we use some of the metrics that we get from the benchmarking suite from running these Hamiltonians in various devices. And at least like in this part, we try to compare the execution time and elapsed time on the basis of like how many numbers of qubit we are using for that specific Hamiltonian. So what elapsed time means is the time that includes all the overhead plus execution, and execution time just means the time to run the core computation. So we ran these Hamiltonian, we ran the transverse field Ising model in 3 different devices. The first one is Blue Qubit CPU, the second one is Blue Qubit GPU, and the third one is an actual hardware device, and that is IBM phase. And you can see in the graph on the right that the execution and elapsed time for these 2 simulators, Blue Qubit CPU and Blue Qubit GPU, they increase exponentially as you increase the number of qubits. But for hardware device, the IBM phase device, the increase is negligible. And there are 4 different crossover points that are marked with a red cross, and those points indicate at what number of qubit do this hardware device outperforms these classical simulators. And these are very like high performance simulators, and this is something we already know theoretically. Like simulators should take more time than the hardware, but this graph just quantifies what we already know. Moving to the next slide. So we have talked about all these Hamiltonians, but why are we interested in it? So I think this slide and what I'm going to talk about over next few minutes is going to make things more realizable in terms of its application. So Hamiltonians, they mean energy, but also other kinds of observables can be derived from a particular Hamiltonians. And those observables can denote some other kind of physical realities. For example, force, or some spin correlation, or some magnetization, and these are the observables people might be interested in. For example, someone interested in drug discovery, they might be interested in forces between all the molecules and so on. So we want to not just calculate the energy, but we can also we want to also calculate the other kind of observables that we can derive from Hamiltonians. And if someone is not from quantum mechanics background, then observables mean something that we can calculate, or at least like measure and get some physical meaning. The equation that you see in the picture is for Heisenberg Hamiltonian, and these are the equation just gives you what are the gates that you apply to which qubit, and there are also other observables like mean spin correlation and magnetization that you can derive from the Hamiltonian, and these observables commute with the Hamiltonian, and there might be other non-commuting observables, but it depends on like what you want to extract from the given Hamiltonian. Moving to the next slide. So whatever you saw earlier, that can be represented in terms of a dictionary that has all the Pauli gates to be applied, and the coefficients, which mean the rotation angles. Just for simplicity, I had like used the values for edge, all those like interaction terms and constants to be 1. And the way we calculate the expectation value of the observable is what we do is, so we simulate the circuit for time t using trotterization that Sunny talked earlier. And for n number of these terms in Hamilton, the edge terms. So in this Heisenberg term, you can see like there are at least like 1, 2, 3, 4. It's like 20, 25, something like that terms. And what you want to do is you want to create the n copies of these circuits. And for each Pauli term, we append basis gates at the end to measure everything on z basis. If there is something like x in the term, then we want to append the Hadamard gate at the end to make everything measured in z basis. And we get all the distributions, and there's some way to calculate the expectation values by calculating the parities. And this can be achieved by using Qiskit's estimator class, but we also wanted to build it ourselves just to understand it more better. And we hope to do some detailed analysis of the calculation process. Next slide. And if you run the Heisenberg model for time 30 time units, then for that model that I showed earlier, this is what it looks like for Trotter steps equals 0.1. And there are some other observables like spin correlation and magnetization. And there are also these theoretical values. If you see on the top, like the blue oscillation denotes the energy, and the red straight line is the theoretical energy. And next slide. So we were also interested in like seeing how things change when we change these Trotter steps. So we varied all the Trotter steps, and we had at least like for the purpose of demonstration, we had 4 different values of Trotter steps: 0.1, 0.25, 0.5, and 1. The first one is for Trotter step 1, and as you can see, like it's really zigzag. And as you make the Trotter steps smaller, it's getting more closer to the theoretical expectation value. And while obviously we want to get something that is really closer to the theoretical value, but there is also a huge cost to pay. That as we decrease the number of trotter steps, we increase the circuit depth, and that will impact the fidelity. So we want to find a right balance of the trotter step and the circuit depth, so that we find a good quantum circuit that does not have too much of depth and that does not have too much of oscillations either. So too much of the uncertainty in terms of the closeness, or the closeness between the expectation and the theoretical and the exact value. So next slide. And earlier I mentioned that for edge terms, it might be 20 terms, it might be any number of terms, and as you increase the number of qubits, there are going to be more strings in each term. So we wanted to find a way that optimizes the way of calculation of the energies and the observables. And for n number of terms, we need n number of copies of the quantum circuit. But there are also other ways that you can group all these Pauli terms to measure things on X, Y, and Z basis that requires a lesser number of quantum circuits. And that is something that we are investigating now, and we want to work further on this field. Next slide. So future direction, we want to analyze other modes of calculating fidelities. We mostly talk about the Hellinger fidelities that relates to Hellinger distance, but there might be other ways that we can extend our work that compares the fidelities for observables. We also want to further analyze the differences between method 1 and method 3. We want to calculate the process fidelity for mirror circuits, and definitely we want to integrate more models of these of the new Hamiltonians in our benchmarking suite. As I talked earlier, we want to implement the optimized calculation method for calculating the observables in the benchmark, and we want to use Hamlib and method 3 for other varieties of algorithms that we already have in our benchmarking suite. And finally, user should be able to run the benchmark on their own hardware, as Sonny mentioned earlier. Next. And at the very end, thank you so much, everyone. Thanks to Tom Lewinsky, Jonathan Feldbringer, Sonny Kazori, Timothy Proctor, the entire Hamlib team, the members of the Standards Committee, QED-C, and SRI International for providing us this really big opportunity to work directly in quantum computing. And thank you so much, everyone who are here, for supporting us directly or indirectly. Thank you. And
Please
if
join
there
me
are
in
any
thanking
more
our
questions,
interns.
yeah.
And we
If
do
you
have
have any
time for
questions.
questions. I see we've seated several questions in the chat, but perhaps we'll invite anyone to unmute and ask their question. We'll address those in the chat as they come up. And if people are able to stay into the top of the hour, we will stay until everyone's questions are satisfied.
I got a question that wasn't in the chat. Nice work, everybody. You know, exciting to see these benchmarks get refined, and yeah, it's cool work. So at different points, I think, can't remember who mentioned it, that these Hamiltonian simulations only have the periodic versus non-periodic parameters, like for transverse field Ising model. There's also, relative strengths of these different, interaction versus the transverse field that has implications for, different like studies people do of these different Hamiltonians. Have you investigated, you know, kind of those ratios at all, or is there like defaults from Hamlib that are required to use?
So far, the parameters that we have considered are the parameters that are there in Hamlib. So
Okay,
for
cool.
AFIM, it was those two.
Okay, and then I guess there's also like different dimensions, right? There's like 1D versus 2D versus 3D. Is it all 1D in this case?
It's all 1D in this case, yes.
Okay, cool. Yeah, it might be interesting to like play with those parameters. I think I'm not an expert in any of this, but I know people I work with like think about, you know, different regimes of these ratios of fields, and also you know, 1D versus 2D has, you know, interesting simulation implications. So cool, thank you.
Yeah, Don Camps, who was one of the creators of Hamlib, just put something in chat about the ratios, Charlie.
There are ratios of like age, but the ratio we did try experimenting by changing those ratios, but what I wanted to say is that it does not have that much effect on the fidelity for either of the methods.
I think you had a question, David?
Yeah, no, first of all, I really want to thank all three of you for the presentation. It's actually great to see how far you've come along from what was a very nebulous idea at the beginning when I brought up using the Hamlet into actual numerical results. So this is very, very exciting. The question that I have is about next steps. What do you think are parts that are still missing or that need some work before, and what is the final product? Should this be aimed as an academic journal, or should this be left as a repository for everyone to use? Do you want to incorporate other hardware? Where is this heading on to?
I think I can comment on that a bit. There's a lot to answer what you asked in terms of next steps. First thing is we want to finish up the work that the interns did over the summer. They're going back to their schooling, and so that project is coming to an end, and we are planning to put out a paper to document it. And as I mentioned in chat, that will largely include all the work on the method variance and the execution time analysis and the basic work to integrate Hamlib. So that will be wrapped up. Following that, we have been having discussions with Don Camps as well as others in the Hamlib group. I would like to see this evolve. A lot of the work that Anish started on the observables and energy is that's just in its beginning. And so I would like to see that evolve further. The Hamlib group put out a paper about their vision for a complete Hamiltonian performance benchmarking suite called HamPerf. And I would really like to see that take shape and support that, possibly building on top of what we've done. All that needs to be explored.
Really great, thank you.
I see Don is on the call here. I don't know if you want to add to anything that I said there. I know I've been very impressed by what you guys have put together, and certainly would like to see it evolve further.
Yeah, no, I fully agree with that, Tom. I've been very impressed with what you've achieved over the summer with a team of interns. It's been great having these discussions, and I'm looking forward to continuing them to see how we can build on top of what you've already established.
Yeah, so I will be, seeking collaborators on the next phase of this project. All right. Well, once again, I want to give a big shout out. It was absolutely fantastic work over the summer, and I think the results show it, speak for themselves. Look forward to seeing this continue to evolve. Thank you, Avamita, Sunny, and Anish.